Hi, my name is Adelbert Chang. I am a data engineer at Target, where I work on deployment infrastructure for the data science and optimization team. And today I'm really excited to be here to talk to you guys about Nelson. Nelson is a deployment system that was originally developed and open sourced by Verizon Labs. And it's something that I've been working on and with myself for the past couple months for my team at Target. My interest in Nelson, to sort of set the stage, my interest in Nelson and the general area of deployment infrastructure came from something that had been bothering me for a while. I think as Scala programmers, and perhaps more generally as functional programmers, we spend a lot of time and effort focusing on the correctness, modularity, and overall ability to reason about our code. If we look over the past couple years at the trends in the open source community or at talks at conferences like Scala, we can see maybe several years ago we started looking into these maybe abstract concepts of like functors, applicatives, monads, and then from there we started actually applying them to help us really reason about and compose our code, such as techniques like free monads and finally tagless, streaming I/O, all the way to recursion schemes. And I think in general, it's really good that we focus on a lot of these software engineering techniques to really make sure our code does what it does. But oftentimes I found when it came time to package and deploy our code, there was sort of this line between our nice, beautiful code and then the often messy, mutable, complex world of builds, deployments, and infrastructure. And this often motivated people, I found, to sort of focus only on their code and punt or otherwise ignore thinking about packaging and deployments, which I think as software engineers, we do need to care about them. So around the middle of last year, when I joined Target and was sort of thrown out of Kubernetes cluster and was like, figure out what to do with this, I had new opportunity as well as new motivation to think about how do we want to actually build these systems and make them nice or as nice as possible and try to sort of make everything nice to reason about from the code all the way to deployment. So I started by asking myself a couple questions. The first one, to sort of borrow terminology from Fred Brooks, was were the complexities associated with packaging and deployments accidental complexities or essential complexities? And then could we then use functional programming techniques that help us reason about our code and apply them to these systems to sort of eliminate some of these complexities? I certainly didn't think we could eliminate all the complexities associated with these. For example, especially in the deployment infrastructure space where we're deploying live systems connected by network, we have all the usual difficulties associated with distributed systems. But I did think that we could, with some work, eliminate some, if not all, of the accidental complexities. Now, on the build and packaging side, there's been some interesting developments over the past several years. So tools like Nix and Bazel take a lot of inspiration from functional programming and apply them to packaging to give us reproducible and deterministic builds. So my team at Target uses Nix for most of our software development, and Nix really takes a holistic approach to applying functional programming to package management, from the lazy functional language that it actually uses to describe builds to the way it tracks package dependencies between packages. On the deployment side, I think is where Nelson sits, and it was sort of what makes me most excited about a system like Nelson, is that it's one, if not the only system I know of that sort of applies a very, like it sort of takes ideas from functional programming, applies them to deployments, and tries to push it forward as hard as it can. And in general, I think it represents what deployments can look like in a more sort of immutable functional programming flavor. So before I sort of dive into what Nelson does, I want to talk a little bit about what I often see as the status quo or what is often done at other companies I've seen. So here we have like a service call graph where the nodes represent services or microservices, if you will, and then the edges represent dependencies. So for instance, service B depends on services D and C for its functionality. And at some point, the service owners for service D want to do an upgrade. And typically this upgrade is done in place. And so maybe they'll do like a rolling update, but at the end of this transition period, where the old version of D lived, there's now the new version of D. And the effect of this is that the entire service call graph, once the new version of D is deployed, sort of observes this change whether or not they're ready. And at scale, it becomes really hard to sort of coordinate with everyone who depends on your service and make sure your new version doesn't break some subtle semantics that one of your dependencies depends on, or one of your dependents depends on. And for those of us who have like deployed large services in like very large scale or in messy environments, we all know that this often can cause outages that we didn't plan for. And I think or at least one of the core problems associated with this mutable deployment model is the mutation part, where we sort of talk about microservices where each team sort of manages their own services, but when a team is ready to upgrade their service, all the teams have to sort of just observe these changes whether or not they're ready. And I think this is a very similar problem with mutable data structures in a concurrent environment, where each individual service or service owner is sort of like a separate thread of control, and then each service location is a mutable reference cell. And so when we do a new deployment of, say, service D, we sort of do it in a mutable way in place, and then all the other threads have to observe these changes whether or not they're ready. So how can we apply a more functional programming flavor to maybe try to solve this issue? Well, the first thing we can do is get rid of the mutable part, right? Let's see what immutable deployments might look like. So same service graph, and we want to upgrade service D again. But this time, instead of doing an in-place deployment, an in-place replacement of the old version of service D, we're going to deploy it just somewhere else, but alongside service D. So even after D 2.2 is done deploying, the new version and old version are coexisting. Services E and B are still pointed at the old version because that was sort of the point of this exercise, right? They're not ready to switch yet, and so they're pointing at the old version. The old version still exists. Everything is fine. Then when, say, service E is actually ready to observe the new service D, E will actually redeploy a new version of itself that explicitly points to a new version of D and then maybe the old version of F. At this point, there's also a new version of service E and an old version of service E, intentionally. And at this point, we sort of have a way of saying, like, is the new version of service E okay? We could maybe deploy it for a couple minutes, couple hours, couple days if we wanted to. And if everything looks good on a new version, then we can go ahead and shut down the old version. Of course, if anything looks wrong with the new version, then we simply shut down the new version, and the old version was always still there, pointing at the exact same dependencies, and everything should continue to work modulo network and the usual distributed system problems. So this is a new state of our graph. And so now we have service E, who was ready to switch, pointing at the new version of service D. And then we have service B, who's maybe not ready to switch yet, pointing at the old version of service D. And this is completely fine, right? This is sort of one of the reasons why we started thinking, like, what would immutable deployments look like? People switch when they're ready. Then service B, let's say, is finally ready to switch. So they deploy a new version of themselves, asking for the new version of D and the old version of C. And then because A depends on B, A will redeploy itself that points at the new version of B. And just like before, if at any point service A or service B decides that the new deployment looks kind of suspicious or something can go wrong, they can just shut down the new version, and the system graph for that particular service sort of looks the same as before. But if everything goes well, then they can shut down, say, the old version of service A, and then we can also shut down the old version of service B, which then also makes the old version of service D eligible to be shut down. And so at every step of this deployment process, we had a transition period where we had the new version and old version coexisting, and we had an easy rollback plan if things went wrong. And I think this way of managing services is very similar to how persistent data structures work in functional programming. And I think just like how persistent data structures give us a very nice vocabulary for talking about changing data, I think immutable deployments can give us a nice vocabulary for talking about service deployments. So now comes the question, how do we actually implement this, right? It's easy for me to stand up here and talk about immutable deployments and service call graphs and nodes and edges, but at the end of the day, we need to actually implement this for this to be useful. So we can start by identifying that at the core of this proposal is this idea of explicitly tracking versions dependencies. Now, in a mutable deployment model, services will have multiple versions, but they tend to live in one fixed location. And so even as services upgrade their versions, they just, at the end of the day, they live in the same location, which makes it easy for other services to refer to these services. They can just be like, give me service a.production.whatever.com. And as service A upgrades, it will just always live at the same address. And that makes connecting to these services easy, right? They just refer to this location either in configuration, or if they're maybe slightly fancier, maybe they have it in some service discovery system like HashiCorp console or something. In an immutable deployment model, we have potentially multiple versions of services. So we no longer have like a fixed location that we can refer to. We no longer can say, give me service A.production. We have to say, give me service A at some particular version. And because new versions will always be deployed, and because there's no sort of one blessed version that everyone should refer to, there's no longer a static address that we can refer to services at. We have to, these addresses are not dynamically determined, and we have to be able to sort of dynamically figure out where they are. And perhaps to make things a little bit more complicated, different versions of the same service can have different versions of different dependencies. So we need to be able to connect specific versions of services with specific versions of the dependencies. Additionally, to make immutable deployments tractable at scale, we need to have some notion of being able to indicate or actually perform a shutdown when it's safe to do so. Right? With multiple versions being deployed at any given time, we'll have old versions of services that may be relied on other people, and as other people sort of migrate to new versions, we have to be able to say, okay, now we can actually, it's safe to shut down the old version, so we can say reclaim resources from our cluster. So one of the ways we could implement that, which seems very difficult at first, is to actually implement this inside our deployment system. So since every deployment or every service deployment flows through our deployment system, it's sort of in a good position to know what services are being deployed, what versions being deployed, and what versions of the dependencies they need, and sort of track and publish that information. And here we can see maybe another idea that we can take from functional programming is to take something that's usually invisible or ambient and reify it into a structure that we can actually work with and query and manipulate. So oftentimes service discovery is separate from deployments. So sort of the service call graph is invisible to the deployment system. The deployment system is sort of just in charge for pushing the tarball or the jar or the container or whatever out to the machines, and then it's done. What we want is for the deployment system to be call graph aware, or what I like to refer to as reifying the call graph. So what we're going to do is require that, when we implement this, is require that every service that flows through our deployment system declare the name and version of itself and of all of its dependencies. And as services get deployed and declare these intentions, the deployment system can build a graph and also publish information like service discovery information, manage the graph to help with, say, cleaning up old versions of services. Now, one thing we need to be really careful about, especially to that last point about cleaning up old versions of services, is we need to make sure that the deployment system actually knows what the graph is. And specifically, we need to make sure that services who declare the dependencies aren't lying about what the dependencies are. So for example, if service B only says it depends on services C and D, we don't want it to somehow also depend on G if it somehow has some out-of-band way of determining where a specific version of G lives, right? Because if, say, service F stops depending on G, then we want the system to be able to say G is safe to shut down, and with some confidence that, say, some rogue service B isn't implicitly depending on it. And so one way we can solve that problem is to use sort of dynamic authorization techniques, which I'll get to in a little bit. So this emphasis on immutable deployments and sort of reifying the service call graph and tracking the graph explicitly, I think, forms the core of Nelson. And everything that Nelson does, I like to think of as consequences of these ideas. In general, I like to think of Nelson as sort of starting with the idea of immutable deployments and sort of pushing it and taking it to its logical conclusion, layering on top of it a lot of necessities that we need to make it actually work at scale, such as lots and lots of automation, especially with regards to managing the graph, garbage collecting old service versions. So let's see how Nelson actually implements these ideas. So earlier I mentioned for our deployment system, we're going to require that every service declare the name and version of itself and all its dependencies. In Nelson, these take the form of manifest files, where we have one manifest file per service we deploy that declares the name and version of that service, which is sort of like a logical name and a logical version, and then the deployable that actually is the deployable unit of that service. Nelson, I think, currently only supports Docker images, but more could be added in the implementation. Then we also have a separate manifest file that actually describes how we deploy each of these individual services. So these describe things like the health check, the number of instances we want, and more importantly, the dependencies, which, as we see here, declare the name of the dependency and also the version. And so these get submitted to Nelson. And when Nelson receives these manifest files, it takes that opportunity to first parse and validate to make sure everything sort of looks correct, all the fields it wants are there, make sure everything's internally consistent. And then it can also undergo some setup associated with it. So It can take like the dependencies list specified here, parse it, figure out what all the dependencies of the service are, and create some sort of dynamic security policy that matches this dependencies list. Now, specifically, these manifest files live in GitHub or GitHub Enterprise, right? Nelson, out of the box, supports GitHub or GitHub Enterprise. We have some work being done by the open source community to support GitLab and potentially like Atlassian Bitbucket. Now, the benefit of having the manifest files actually in version control is sort of the usual reasons why we have code in version control. We sort of, if we have a deployment tied to a specific commit and say Git, then we can go to that commit and figure out what code was deployed, how it was deployed through Nelson, and if we're using something like Travis or Jenkins or Circle CI, we can also see what criteria allowed it to pass CI. And so now we have like a history of not only of how our code grows, but also how it was packaged and deployed. Another benefit of using a VCS platform like GitHub is it allows Nelson to use features of that platform. So Nelson specifically uses the GitHub release feature. So what happens is when in order to deploy something, an actual GitHub release is made. And that GitHub release will then fire a webhook at Nelson, which sends a webhook event, which signals to Nelson to actually go back to the corresponding repository, find these manifest files, and then parse them. A benefit of doing that is it also allows people to sort of have a continuous deployment model, where maybe as part of your CI, you have you run the tests and everything looks good, and then you build and push the Docker image to something like Artifactory or some Docker registry, and then you cut a GitHub release. From there is where GitHub takes over. That release event gets fired at Nelson. Nelson will then go back to the GitHub repository, take the files, and do its thing. So we can sort of have a notion of continuous deployment as well. So once Nelson receives these manifest files, it'll start working on them to do the actual work and deploy. So the first thing it'll typically do is to generate a dynamic security policy. Out of the box, Nelson currently only supports HashiCorp Vault, but it's relatively easy to extend this to other systems, and I'll get into that in a bit. So the effect of writing a dynamic Vault policy associated with the dependencies list is your system basically can only get as many access tokens as you specify dependencies. So if you have if you try to call a service that's not specified in your dependencies list, then you don't get access to that token as part of your security policy. And so even if you somehow figured out where that service was, you couldn't talk to it. This is of course subject to making sure your systems actually secure themselves, but this is sort of the assumption that Nelson has to make sure people don't lie about their dependency graph. After generating the dynamic security policy, Nelson will also publish service discovery information to a system like HashiCorp Console. Again, out of the box, Nelson currently only supports Console, but more can be added. And then finally, it will actually deploy it into a cluster schedule like Kubernetes or HashiCorp Nomad. So that's how Nelson creates the graph, or actually deploys something. Let's see how it actually manages it now. So besides deploying, Nelson will also always do things in the background. So, excuse me. The first thing Nelson sort of does besides deploy things is it has this idea of traffic shifting. So earlier when we initially started talking about mutable deployments, we noticed that for every new deployment of a service, we sort of have to redeploy all the dependents of the graph. So let's say we deploy a new version of C. Then in order for B to observe that, B has to redeploy, and in order for A to observe that, A has to redeploy. And so this is good for making sure that people only transition to new versions when they're ready, but it could get very tedious, especially at scale, where for every small change, especially in like a continuous deployment model, people would need to redeploy in order to observe these small changes, which can get really annoying, really tedious, and will sort of make people frustrated with the system. So as an optimization to avoid this problem, Nelson, Nelson actually understands the ideas of semantic versioning. So it understands major, minor patch versions, and it understands that for patch versions specifically, new bumps for patch versions are backwards compatible or semantically compatible with previous patch versions. So in the case of the new deployment of C, which is a patch version update, instead of requiring a redeploy for services B and A, it will actually just sort of indicate that, hey, B, you can traffic shift to this new version because this is a patch update, and so it should be safe for you to traffic shift over. And so assuming things go well, B will then, at the end, point to the new version of C, and then the old version of C is eligible to be shut down. For major and minor versions, of course, we still require, which signal like slightly more complicated changes, we require people to redeploy. If at any point during the traffic shift things sort of go wrong, which they often do, Nelson does provide a way for service owners to reverse the traffic shift through a CLI, and then that would make people continue to point the old version, and then the new version would eventually be eligible to be shut down. And now service owners are sort of free to make simple version bumps or make small iterations without having to worry about creating this worrying, cascading deployment effect across the entire service graph. Another thing that Nelson does, and that's probably one of the most important things it does, is it has this notion of graph pruning, or automatically shutting down old versions of the system. So with immutable deployments, and especially with continuous deployments, there's going to be lots of different versions of different services constantly being deployed. As services redeploy, they'll move to new versions, and we need to have a way to automate when, not only when it's safe to shut down an old service, but also to just actually do it. Because if we leave it to service owners to do it, it takes time out of their day, it can get tedious, and if Nelson already knows it's safe to shut down a service, then it should just go and do it. Now, given just a service graph as is, as I've described so far, Nelson doesn't actually have enough information to know when a service is safe to be shut down. Even if the graph were to say be disconnected, that doesn't really signal anything. It just might mean like we have some anchor point in the graph where different services are depending on old version and different services are depending on a new version. So to solve this problem, Nelson actually uses an existing concept I haven't mentioned yet, which is the idea of a load balancer. So a load balancer serves two purposes. One is to sort of actually provide load balancer functionality, which is to say expose this service to the outside world so people can like visit your web page or hit your API or something. Separately, it also serves as sort of roots of the service call graph, where if you imagine sort of like garbage collection and memory managed languages, we have like roots or references that we are currently active. In Nelson, these are sort of like load balance services. And so what Nelson will do is it'll start from these load balance services and traverse the entire graph. And nodes that's not able to reach, it will deem as saying it's not doing any useful work, and so it should be safe to shut down. So as an example, let's say we deploy a minor bump of service F, which doesn't depend on G. Since it's a minor bump, we're going to redeploy E. And at some point, we decided it's safe to shut down the old version of E. Now, at this point, at the next GC pass, as you might want to think about it, Nelson will start from nodes A and E and sort of traverse the graph and notice that the old version of F and services G are no longer reachable from the load balancer. And so it'll go ahead and mark those as garbage, and then we'll have some separate pass that goes and actually shuts those down. As another example, let's say we do a patch bump of version B. A will traffic shift over to the new patch bump of version B, assuming things go well. At this point, Nelson will see that the old version of service B is no longer reachable, and so we'll go ahead and shut those down. And so here we still have, like I mentioned before, we have a disconnected graph, but the graph will remain as is because the entirety of the graph is reachable from the roots or the load balance roots of the Nelson service graph. So far we've been mostly talking about services, but there's another type of workload that is pretty common, but that isn't sort of subject to load balancing, but we also don't want to garbage collect. And that's the notion of sort of jobs, right? You can think of these as Spark jobs or MapReduce jobs or ETL jobs or whatever. So in order to talk about how jobs are handled in this sort of garbage collection or graph pruning process, we have to talk about expiration policies. And so expiration policies are sort of the thing that actually are evaluated by Nelson to determine whether or not to garbage collect a particular service. So in this load balance environment, it's under the expiration policy called retain active. What I'm about to describe for jobs will be other expiration policies. You could apply the expiration policies I'm about to describe to services. It's just seldom done, but nothing's stopping you from doing it. So the first expiration policy I'm going to talk about is the retain latest, which is sort of maybe you can think of as the one that most mutable deployment models employ. So we start with the version X, maybe 3.2. We do a patch bump or whatever. Nelson will shut down the old version and keep the new version. Then we do another version bump. So it's using the new version, next GC pass, it shuts down the old version. And then so on and so forth. So just retaining always the latest version of the job. And it does this by using the same sort of, I understand, semantic versioning model as it did for traffic shifting. Nelson also has a couple other expiration policies. Two of the more interesting ones are retain latest to major. Sort of confusing here. So semantic versioning traditionally marketed as major, minor, patch. I believe Nelson refers to these as feature, major, and I guess patch. So here, retain latest to major is really retain the latest to semantic minor versions. And so as time goes on, you sort of just keep track what the latest versions of the two major/minor versions are and keep those and shut down old versions of the latest two major versions as needed. And then there's also retain latest to feature, which is similar to latest to major, except it works on the semantic major version of the service, of the job. So going back to our earlier example, let's say we have job X version 1.8.5, and let's see what happens when we apply the retain latest to major policy on it. So we deploy a new version of job X that's 1.9. And at this point, things stay the same because we're retaining the latest to major. Then we deploy a new version, a new patch version of the 1.8 series. And at this point, Nelson will detect that for one of the major versions it's keeping, there's a new version of it. So we'll shut down the old version. And then let's say we deploy 1.9.1. And so it'll shut down the old version of 1.9.0. But at any given point, it will keep the latest version of the two major versions it's keeping track of. So that's how Nelson works at a system level. We saw what Nelson does at deployment time and also what it does when things aren't being deployed sort of in the background. So now I want to show you guys how it's being implemented. So the code I'm about to show is code that I've more or less copy-pasted and then sort of stubbed out with like triple dots when it didn't fit on the slide, but this is like actual code that's inside the Nelson code base. Specifically, this is the one that corresponds to the Nomad scheduler. So you'll see stuff that maybe doesn't make sense for Kubernetes, but the general idea is the same. So we start off by sort of getting the Docker information from the specified image at deployment time. This is the code that's run when we actually deploy something. It will then it'll take sort of the plan and write alerts to HashiCorp console. It will then generate and write the dynamic security policy it creates to HashiCorp Vault. And then it will write service discovery information to console, get the traffic shift associated with it, and then actually launch the image on Nomad. For deletion, this works largely the same, except in reverse. When it deems a specific service or job eligible to be shut down, it will launch the deletion. It'll run the deletion workflow, which will delete the dynamic security policy from Vault, delete the alerts from console, delete console discovery information, and then actually delete the image on the scheduler. Now, you might feel like I'm sort of been cheating with this code because like it's very high level and it sort of matches what I've been describing with how I describe the system. But I'll get back to that in a bit. But this is the actual code that's being run by Nelson, and I'll show you what's backing this code after I finish the next slide. So for background processes, Nelson also, so this is the stuff that sort of runs in the background when Nelson's not deploying stuff. So Nelson will run, so these background jobs are streams, like Scala-Z streams, that are continuous like polling or publishing information. So one is the auditor that sort of provides audit log information for like why Nelson launched or deleted a particular thing. Pipeline processor is what actually does the launch workflow, so it listens for like GitHub release events and runs it through a pipeline. Workflow logger is for logging. Routing cron is what publishes service discovery information out of Cadence. And a cleanup pipeline and sweeper are sort of what do the GC passes over the graph. And then the deployment monitor is what just like monitors health checks to allow people to sort of see like, are all my services healthy? Yeah, so all of these things so far are like very high level ideas. And so something has to be backing them that actually does the work. Well, perhaps one of the a really fascinating thing to me about Nelson is all of these things are backed by co-products of free algebras. And so they're they're extremely abstract things. By themselves, they don't really do anything. They're high level because the algebras we're working with are more or less high level. So earlier when I talked about launching and deletion workflows, those have type workflow F of unit, I think. And so our workflow F is sort of composed of these very abstract free algebras that can talk to Docker, can talk to console, can do logging, talk to the Nelson database, and can talk to a scheduler. And everything in Nelson sort of is programmed against these very abstract interfaces. And what actually makes them go is a bunch of interpreters that sort of actually interpret them into things that do useful things. So when you run this in production, we have some interpreters that will take Nelson configuration and parse them into these interpreters, and then actually like say when you say launch, you mean launch on like Kubernetes. And when you say write dynamic security policy to vault, you mean like hit vault at this particular API with these values. Now, a nice part of this is in testing, if you look at a Nelson unit test, we can also, because everything is sort of programmed against these very abstract free algebras, we don't actually have to sort of launch a test Kubernetes instance or launch a test console instance in order to, say, make sure our garbage collection algorithms work. Because what we can do is we can just generate, say, instead of deploying console, we can just have like an in-memory map of like keys to values that we can populate in memory, and our interpreter is just like, instead of deploying a test instance of console and writing to console, we just like populate the map in memory, and then we can test to make sure a lot of the core functionality of Nelson is sort of sound and does what we want with like minimal work, right? Because everything in Nelson is sort of programmed against free algebras, and the only thing that makes them actually do work are these interpreters. So I think that's really cool. So because everything is abstract, I mentioned earlier that out of the box for security policies, we support HashiCorp Vault. For service discovery, we support HashiCorp Console. And then for schedulers, we have Kubernetes and HashiCorp Nomad. But nothing is it's relatively easy to add support for other systems as we see fit. And so when I added Kubernetes support a couple months ago, I pretty much only had to touch the scheduler algebra part of it. I didn't really have to care how Vault worked or how Console worked or how sort of the garbage collection mechanism worked. I just implemented the Kubernetes interpreter, and everything sort of just worked from there. As for implementing alternatives to Vault or Console, we've been talking about using something like Istio, if you're familiar with that. And in order to support that, it would just be a matter of adding support, creating an Istio interpreter for the Vault and the service discovery algebras. And the way we're sort of handling the version control support problem is that we have like a VCS algebra that we could create. And then people would provide a GitLab interpreter and a GitHub interpreter and maybe a Bitbucket interpreter. And one of the wacky things you could do if you really wanted to is you could just have, so Nelson supports this notion of like managing multiple data centers. And so if you wanted to, you could have one data center run like Kubernetes console Vault, another data center run Nomad Vault console, another data center run Kubernetes Istio. A couple weeks ago, I was potentially going to add, for one of our DCs, which runs MapReduce jobs, to run an interpreter for Hadoop Yarn. And that wasn't like a scary at all prospect for me because I knew doing that for Nelson would just be to implement the interpreter for Yarn, for the scheduler op. So I think that's really cool. So have we achieved our goal, right? The initial goal of this was to take something that was packaged, in our case a Docker container, and deploy that in a sort of a nice and reasonable way. So we started off by sort of saying we're going to, instead of doing mutable deployments, we're going to do immutable deployments, and to do that, we're going to reify the service graph and sort of have this persistent data structure-like method of managing deployments. From there, that influenced how developers actually work with the system. It's a very GitHub-driven system where everything's sort of checked in, and sort of trigger point is GitHub release, which makes it not only easy for us to sort of debug how deployments change across history, but also like a couple weeks ago, for my team, we wanted to cut a new GitHub release, but not actually trigger, but sort of like just ignore Nelson for while we were debugging something. And so we just had to sort of disable the GitHub webhook, and so the rest of our pipeline just worked as is, but it just didn't talk to Nelson. And when we were ready to start it up again, we just re-enable that webhook. So our decisions sort of led us to influence how our developers work with our deployment systems, and then we ended up with a deployment system that sort of did what we wanted. One thing I didn't mention that I want to mention really quick is earlier when I said Nelson publishes information to Vault and console, at no point did I say like Nelson will then go and dynamically render secrets inside the image, or it'll try to connect services with each other automatically. This was a conscious decision by Nelson, and I like to think of it also as another application of functional programming, which is Nelson intentionally does the minimal amount of work that it needs to allow services to get their job done. So Nelson is sort of like, here's your security policy and it lives in Vault. Here's your services information, it lives in console. It is up to the services to pull this information and actually consume it. That makes Nelson's job easy. That makes sure that anything that Nelson isn't too prescriptive of how services consume this information, and it also takes Nelson out of the firing line. Should Nelson go down, services are still able to pull secrets and talk to each other. Nelson is not sort of in the critical path unless you need to redeploy something. But I think Nelson does what it says on the tin. I don't think this is as far as sort of the innovation will go, but I think as far as other deployment systems I've seen, Nelson represents a very interesting approach to deployments. We've had it deployed on my team for a while now, and it sort of just works, has caused us no issues at all. And I encourage everyone to sort of, if you're interested, come talk to me, come join us. We have a website, we have a GitHub organization, and we also have a Gitter room that you can come and chat with us about it. But that's all I had for you guys today. Any questions? Don't know your names, but I guess like the guy at very far back.
So you mentioned that you'll shift to a new pattern version. A minor version should also be backwards compatible, and often major versions aren't going to interfere with your particular path, so you can upgrade nicely. Have you thought about maybe speculatively spinning up new versions of all of the things that depend on you, and then having it automatically run all of your integration tests and all of that stuff on those things, and maybe like emailing the maintainers to let them know that everything worked and you can.
So the question was, have we thought about doing something like automatically spinning up the new versions of like our dependents and sort of running their integration tests to make sure everything is okay, and sort of doing that, doing traffic shifting that way? Is that an accurate restatement of your?
In order to kind of more easily go to the minor and major versions.
Oh, I see. Yeah, so to support traffic shifting in major minor versions and not just patch. Okay. We haven't, and I want to say that's a conscious decision because I think Nelson sort of prides itself on sort of doing the minimal amount of work to do so. I can see the appeal of using that sort of heuristic to help traffic shift to new versions, but I think intentionally right now Nelson doesn't do that because it's sort of tricky to get that right, especially like if you have a large number of dependents, then you can all of a sudden like clobber the scheduler or something like that. Yeah.
One of the things I noticed is, especially with the terminating the nodes or pruning, it kind of depends if the services talk directly to each other rather than having something like a message broker between them. Is there any kind of thought about how or when you support something like that if you had like Kafka or RabbitMQ in between them?
So if we treat them, I see. So one way I can think is if we treat the message broker itself as a service, then it would be, if it was part of the graph, then we would still have that path to the leaf service, I guess. The tricky part is like something like RabbitMQ is not generally something that's subject to the usual service deployment cadence. I think Nelson, I haven't used it myself, but I think Nelson supports the notion of like manual deployments, which is basically it's a system that's handled outside of the graph, but is made aware to Nelson. So you're basically telling Nelson this service exists at this location, but it's not like subject to the usual Nelson garbage collection and stuff. So I think that might be a way to do it. Bonnie, I think?
I guess related to the other questions, what sorts of operational pain points have you seen with using Nelson? So, for example, do you have issues around being able to validate that patch versions are actually compatible? What happens if you need to debug like a minor performance regression or something like
Right, so Nelson sort of just optimistically will traffic ship to a patch version and assume that service owners are not lying about the compatibilities, because there's no, to my knowledge, there's no sort of good way of being absolutely sure and automating a way of saying this is compatible. So that's why Nelson sort of provides, say, if things go wrong, then the service owners can say like Nelson reverse traffic shift, and Nelson will indicate to traffic shift back. And it's
I guess my question is about, given the limitations, what do you expect service owners to do to mitigate that limitation?
So once everything is traffic shifted back, the new version will be torn down, and I guess from there you would fall back to the usual sort of like, all right, let's see what code paths went wrong or what changed. I think Nelson will not do anything to sort of try to, at least Nelson out of the box will not try to do anything to like make it easier, like keep the old version, keep the new version there for debugging purposes or anything like that.
Are there patterns you can follow to prevent Nelson from itself becoming a monolith? For instance, can it read from multiple GitHub repositories, or can you run multiple Nelson instances and have them talk to each other?
It can read from multiple GitHub repositories, because all Nelson itself is waiting for is like a GitHub release event. And so, so Nelson was developed in a poly repo environment. And so all people had to do was basically install the Nelson webhook as part of the GitHub repository. There's a CLI to make it easy to do that, but that's sort of, at that point is what Nelson actually cares about. It doesn't have to, like if we wanted to, we could like manually create a GitHub release event and send that to Nelson, and Nelson would be perfectly happy with that. And so I hope that answers your first question. As for a second question, out of the box, Nelson currently doesn't support clustering. That's a conscious decision, I believe. We could add it, but I think right now, out of the box, Nelson is able to support lots of concurrent deployments if it needed to, and moreover, Nelson isn't, unless like your business is very deployment centric, if Nelson goes down, the services as is will continue to operate. The only thing that Nelson will affect if it goes down is people won't be able to deploy.
When it does traffic shifting, right? So does it do gradually? Like if you feel like cool, right? So does it shift? And then you release this like minor version. So when it tries to like shift traffic, does it do gradually? Like
Oh, like how does it do the traffic shifting?
Like, see how like
Right. So Nelson support. Right. So Nelson supports a couple ways of doing traffic shifting. There's like, you can do a linear where you sort of like doing a linear bleed. There's also like stuff like exponential bleed or logarithmic bleeding of traffic. So there's certain pre-configured like patterns that Nelson will support that inside the manifest file actually, I think. You could say like, for my service, I want to bleed traffic in this way. And so when new versions spin up, that Nelson will use that information to decide how it bleeds traffic.
One more question, like what is the scale of your services where you use it?
The way my team uses it is very small, so we just have a couple services and like 1 or 2 nightly jobs that we run. So for my team, it hasn't been tested at scale, but also I think that speaks to like Nelson. Something like Nelson was, initially I thought it'd be like a very big system. It was designed for Verizon Labs where they had like hundreds of microservices, and so it definitely worked at scale. But I think it's also a testament to how Nelson was designed that for my team, where my operations team is like me and 1 other person currently, we still operate it and it doesn't really cause us any frustration. So it works, it's definitely been worked at a large scale at a company like Verizon, and it's definitely been working for us at a small scale.
This stuff.
We deploy Nelson for my team. To be clear, I don't work for like Target. I don't handle Target.com. I work for like a very small team within Target that does the supply chain stuff. So my team, to answer your question, we've deployed Nelson officially about 3-4 months ago. And so we initially started with like 1 job. We initially like manually deployed this 1 job through like explicit Kubernetes YAML files, and then we shifted it to Nelson, which has been extremely nice for us. Does that answer your question? Yeah.
Do you use anything like Diesel, I think, to help you with the verbose of declaring these pre-algebras?
Is Diesel like one of those like?
A macro that you annotate things here output.
Oh, so like does the Nelson code base use this?
Yes.
Currently, no. So the code, the explicit co-product code. Oh, no. Yeah. So this is like taken verbatim from the code base. So one of the reasons for that, if you notice, also like the explicit free C, this was written on like Scala 7.1. So it's like an old version of free and everything. Still works, but that's one of the reasons why we don't use those, because those didn't really come out until like maybe a couple years ago. But as we migrate to like a more modern stack, we could consider using frameworks like those.
Can I write the manifest file in Scala?
No, currently the manifest is yet another YAML file for you to maintain. Maybe we could add support for other configuration formats, but currently it's YAML, I think. Cool. Well, thank you, everyone. Feel free to come up to me if you have more questions.